Hi, everyone. Welcome to the kickoff of session number 2, Essential Reasoning Skills for Data Science. We have yet another all-star cast here today. And what we're going to be talking about is modes of reasoning that are extremely applicable to data science. Those modes are deductive reasoning, inductive reasoning, and abductive reasoning. And the reason that I wanted to have a dedicated session on this is because I think data science is one of those areas where in our day-to-day practice, whether we're doing exploratory data analysis, model fitting, predictive checking, things like that, we use each of those modes of reasoning on a day-to-day basis. And yet the terms like induction and deduction aren't actually a common part of the data scientist vocabulary. And furthermore, what I've noticed is that there's actually a bit of a division where if you talk to the highest level machine learning experts or statisticians or data scientists, they actually do use terms like deduction and induction and say, oh, well, this is my inductive component of this, or this is my deductive component so that I know this bit will work or is true. And it's very much a part of the vocabulary of a certain population of our of practitioners. And it's much less used in, for example, early career data scientists and statisticians. And I thought that this is a real shame because language is our way to reason about these things. So if we have these words in our language, we'll be better off and more capable of reasoning through them. Now, in a simple example of this, we've now seen the critical reasoning in data science episode, in which I show how a deductive reasoning failure led me off on the wrong path. Now, I'll stop talking pretty shortly because I've been talking too much, but I'm not qualified to cover this in as rigorously as I'd like to. So I brought on the experts, Elina, Huub, and Joseph. And just as a quick thing, I contacted Elina when I was first trying to put this session together, and she basically said, don't worry, I got this. She assembled her A team of Huub and Joseph, and they put together the session. So I'd like to very much thank Elina for her effort on this behalf. So please clap at your monitors on behalf of Elina now.
My pleasure. Thank you.
Thanks. All right, so I guess let's begin with the conversation. We're just going to have a conversation about this topic, and then it will be followed by 3 very gentle, short introductions to each of these modes of reasoning, which should be very useful. So where should we get started? I think that why don't you each introduce yourselves and the sort of scientific area or social scientific area in which you apply your research, because I think we have a very good coverage there. Starting with Huub, upper corner.
Okay, hello everyone. My name is Huub. I'm an assistant professor at Tilburg University in ethics and political philosophy. I have a background in philosophy of economics. And I'm actually quite interested, so I did more empirical stuff when I was studying economics. And I'm interested in getting back to that. So researching people's intuitions about distributive justice. So that's it.
All right, Elina.
Great. So I'm a philosopher of science, and I am currently a visiting researcher at the Finnish Institute for Health and Welfare. And when I did my PhD, I was focusing on philosophical problems related to psychometrics, which is basically the background theory of all of psychological measurement. And right now I'm generalizing from that, working on more closely on the methods themselves and also writing about them in both Finnish and in English.
Joseph, by process of elimination.
Hi everyone, my name is Joseph. I have a background in the philosophy of science, and prior to this I was doing my PhD in the same department as Elina, working on ethical issues in screening for cancer and looking at the political and ethical issues arising in that public health practice. And nowadays I'm a medical student at Brown, and I'm just trying to learn how to become a clinician.
Very cool. And so I guess one of the key commonalities here is that you're all connected via the philosophy of science department at the other university, otherwise known as Cambridge.
Well, me and Huub, we are from the Rotterdam University. Actually, we know each other from Rotterdam University.
And then our
parts went in different directions, but still we kept in touch and still continue to talk about philosophy of science every now and again.
Yeah.
Very cool. Yeah, it is nice having these dedicated fields to, when by this dedicated field, I mean, I'm talking about just the philosophy of science, and having people dedicate their time to focusing on these like more abstract issues to better understand, you know, how we are in fact practicing these. So again, it seemed natural to me that philosophers of science would be the ones best meant to lead us through this practice. Now, I figured that how should we start? I'm thinking that so I've given out a thesis now, which is that data science has an interesting aspect in which we use inductive, deductive, and abductive reasoning pretty much on a usual basis. But one thing is, of course, that there isn't while there is a very clear understanding about what these different modes of reasoning are, I guess theoretically, in practice, they frequently overlap. For example, in Huub's presentation, he talks about how Sherlock Holmes, the great reasoner, is using abductive reasoning, but he calls it deductive reasoning at the time, just from his own, says he's using deductions. So is it true that in practice, these different modes of reasoning overlap more than we might like, that they aren't as clear-cut as we might like to think?
Okay, so, well, maybe I'll start. Well, first thing to note is that sometimes we, or actually very often we call a specific mode of reasoning by the wrong name. So there are quite, well, maybe not clear cut, but still like more or less clear guidelines for differentiating between deduction, induction, and abduction. Maybe the dividing line between abduction and induction can be sometimes a little bit like this, yeah. But especially deduction is quite clearly separate from those. So, and I think that it can be maybe not dangerous, but it can be can lead to bad consequences if we kind of call, for example, induction, we call it deduction, and then we kind of imagine that some of the nice qualities of deduction also apply to induction. So that's the first thing that I think should be noted about the kind of like overlap that's present sometimes in these discussions. So there's an like kind of the wrong kind of overlap between the ways in which we use the terminology.
Yeah, you've really hit the nail on the head there for something that I've noticed, where people frequently they do treat some inductive element of their sort of data science or machine learning process, and they treat it as some sort of like deductive guarantee. Very quickly, should we just define deduction, meaning that that if the premise is true, that your conclusion is guaranteed to follow from it? What is how should we? I figure we should very quickly define what we mean for each of these terms.
Right. Okay. So deduction. Yeah, that's a good way to think about it. Another way is to think about deduction in terms of rule-based reasoning. So we have these very carefully laid out inference rules, and we can only arrive at valid and sound conclusions by following those rules. And I think that that's one way to kind of differentiate it from the other modes of reasoning, because the rules of making the claims that you want to make are so clearly defined. Yeah,
so for example, mathematics seems to be one of the clearest sort of heavily deductive disciplines, where, and it's one of the reasons why I guess math is so difficult but guaranteed, because they are so rigorous in what you need to make a conclusion. Math is unforgiving in that regard. But at the same time, when something has been deductively proved or mathematically proved, that you do have a guarantee that it will continue to be a valid thing into the future. It doesn't stop being true because of some new component. You know, the mat doesn't shift underneath you in mathematics.
Exactly.
Yeah.
Cool. And now, how about induction? So, Joseph, would you like to define induction and maybe give just a quick example?
Sure. So I suppose in deduction, as Elina was saying, if the premises are true, then the conclusion must be true. Whereas in inductive reasoning, when you have a set of premises, they provide evidence or support for the conclusion. But as a matter of fact, it can still be the case that even if all of the evidence points towards the conclusion, even if all the premises are true, the conclusion can still be false. And so I think a very simple example that many people might be aware of is the results of trials in science. Studies provide lots of evidence for a particular conclusion, but when you're doing the study itself, you're usually or almost always dealing with subjects or participants that aren't the actual people who you're trying to intervene on later on when you implement a particular policy. And so when you're moving from the study context to the actual context of implementation, a number of assumptions that the study relies on might no longer be true. And as a result, the conclusion of the study might not actually hold up in a different context. So that's just a simple example of how when we're dealing with inductive inferences, right, we have lots of evidence pointing in one particular direction for conclusion, but we need to be careful of what assumptions we are relying on when we move to a new context.
Yeah, and I really like your example with the clinical trial, because especially in clinical trials where our conclusion is ultimately, it can frequently be based on a model. It's a good segue, because yes, it is true that we, for a clinical trial, we were seeing, well, does our trial sample represent the more general population? And which is why then we have terms like efficacy and effectiveness, and we consider these to be different things in the clinical trial space. Specifically because there's a difference between the way that the clinical intervention is implemented in a trial versus how it's implemented in common practice. And I guess the reason that I think it's a good segue to the discussion of abduction is because, for example, in a clinical trial, say you fit a Cox proportional hazard model or something like that. And so effectively you are then estimating the effect size. And you're using that estimate of the effect size to decide if a drug is useful in some way. That use of the model is then, of course, is a model fit. It is making inference to the most likely description of the data. I guess that is also an abductive. There's an abductive component that then you use inductively to say that this will be applied to other people. So, Joseph, you always come up with the best examples. You also had that good one with the personalized medicine one. But yeah, that you described in one of our previous conversations. But maybe Huub, do you want to quickly go over abductive reasoning for us?
Yeah, so I would say abductive reasoning is trying to infer to the best explanation of a given set of facts. And the example that I give in the tutorial is of Sherlock Holmes's methods. So Sherlock Holmes often is confronted with a very disparate sets of facts that may lead to the discovery of who has committed a criminal act, but it's very difficult to find a good explanation. And what he's trying to do is to find the best explanation of the facts. And once he's done that, he can usually point to who committed the crime, and that's then the best explanation. This type of reasoning is used a lot in economics, so I'll provide an example of economics as well. Yeah.
Very cool. And I guess one thing that I wouldn't mind circling back on is the fact that you said that inductive reasoning and abductive reasoning frequently are conflated. And I'm glad that that's been acknowledged, because honestly, I use those more or less interchangeably, probably unforgivably. Like I pretty much use the term incorrectly about 50% of the time. Like my batting average is not too good on that regard. But I am glad that I benefited from watching these tutorials, because it helps me better gain an understanding of what I was doing. But why would we think, why is there so much of this conclusion? Is it because we don't really understand the terms as well, or because there is a legitimate philosophical gray area between these? For example, the world's complex, and so when we're talking about an inductive or abductive component of it, it might be because we're focusing on one aspect of a complex system, which it's more inductive. For example, is that a legitimate observation, or are there why does inductive and abduction why are they confused so much?
Okay, well, I can start with my guess of why they might be confused so much. So
Guesses are perfect.
so one thing that comes to mind is that, like, you know, when we have examples of inductive reasoning, it's often the case that we talk about some group of evidence, and then we have one, maybe two kind of hypotheses that we're considering in terms of that evidence, and seeing like what would it take to go from that evidence to that conclusion, or how much of that evidence we need to go into like confirming or corroborating some of the theories. Whereas as in Huub's example, you know, in the Sherlock Holmes case, you might have various different theories, and then you have various different groups of evidence, and then you're kind of like shuffling between them and trying to maybe find a find the most coherent group of both pieces of evidence and theory. So which things go together, and by that method kind of eliminate the bad or the worst alternatives, and then arrive at the best one. So, you know, in both of these, you're kind of like trying to bring evidence and the conclusion into or bring them together, make them compatible. But abduction is maybe just a little bit more messy as a process. So yeah, I would like kind of, and you know, that kind of makes it make sense. That's a reason why you might get confused with them, because they're kind of similar processes, but still a little bit different. Or am I completely off, Joseph?
No. I honestly, my favorite thing was you said, like, abduction is a messy process. It's like, yeah, it's real messy. Abduction is super duper messy sometimes. Knowing to actually how to like infer to the best solution, or if even one. That's why sometimes we like just integrate over our different explanations, and hopefully that they are more cohesive. Did anyone else want to add anything to that? I thought that is a really good explanation.
No, I mean, I thought that was great. I think I will note, I think that one reason it is very slippery is that, you know, there's this problem of induction that some people are aware of, you know, that comes from David Hume. You know, how do we rationally justify induction when all of our inferences have to rely on this assumption that things in the past are going to be similar in relevant ways to things in the future. And so one thing that comes up in the philosophical literature, at least, is that abductive reasoning, or inference to the best explanation, is a potential solution to that problem, where it's just a form of reasoning where if we infer to the best explanation, we have you know, some sort of way to counter the worry that our inductive inferences aren't going to be very stable. And so it's sort of, it could be a strategy to put our reasoning in the world, or about the world, on a firm footing.
Yeah, so I guess there's that quote that says, was it that induction is the jewel of science and the scandal of philosophy? Is that the quote? Where I guess maybe, why don't we hit on the idea, on the problem of induction once again, just in case people sort of missed it the first time, where we have this issue that we are basing, induction requires us to basically base our future expectations on a set of previously observed facts. And what we're essentially relying on is that there's some uniformity to this scientific process. That means that what we observed in the past is actually relevant to the future. Sort of like we saw the sun rise in the east yesterday and the day before and the day before that. Are we going to continue to believe that the sun will keep rising from the east, generally eastward, on a day-to-day basis? And I guess is that an inductive thing? Obviously now we have even more to base that induction on, but you know, even still, if we say we want to look at this from a celestial perspective, we still believe that, you know, the orbit will keep going in the same direction and things like that, that the earth isn't going to just immediately like pull a fast one on us and start whirling in the opposite direction. That is presumably an inductive belief.
Yeah, I think you've described the problem of induction pretty well. So it's the problem that you can never have full confirmation of a theory in light of the empirical evidence that you gather. So the pieces of evidence will never fully clinch the case for the conclusion, but rather you always have to jump over some kind of gap in order to make this general statement or general positive statement, at least, about the world.
Yeah, and then in contrast, for example, deduction, we always know that it will fall through, and so that's we logically know that's going to fall through. One other interesting thing is that since we do come from different applied fields, some varied applied fields, is the actual discipline in which people apply their scientific philosophy or their inductive or abductive philosophy. Does it differ from field to field? For example, where if someone is working in particle physics, are their inductive steps more certain than people, for example, working to discover social scientific phenomena like behavioral sciences? Are there differences in that regard where these different fields they might have different levels of tenuousness, where we can we believe that if some hadron particle collider result is less likely to be overturned by subsequent evidence than, for example, the effect of the Federal Reserve changing the interest rate and how that changes, the GDP growth or something like that. Do these different fields have sort of different inductiveness coefficients where you need to take bigger scientific leaps of faith?
Yeah, sure. So I guess I can comment on that. So I suppose another way to put the question is, look, there's this very deep problem of induction, right? So, philosophers have worried about this for centuries. But then there's a more practical issue of when we have an inductive inference, how certain should we be before we accept the conclusion? How confident should we be before we accept the conclusion? Because, I think in practice, taking the medical field, we can't just sit around all day and saying, oh, well, what if this inference doesn't hold true because of this really deep worry that Hume came up with? It is a very deep worry, but in practice, we need to act, we need to move on. And so, one thing I know Elina knows a lot about is in deciding when to accept a conclusion that is an inductive inference, a lot of it will depend on the moral consequences of being wrong. So, if I'm running a study and acting on a conclusion incorrectly would lead to really devastating consequences. The classic example is if I'm a regulatory agency and I'm deciding whether or not a particular chemical in lots of cleaning products will cause cancer, I should be very, very, very certain that it doesn't cause cancer before I add that chemical to a number of different products. Because if I'm wrong, right, the consequences are going to be huge for public health. And so that's a case in which we're moving from evidence to a policy, for example, and we need to take into account what's going to happen if we make this inference incorrectly. And that therefore also has an impact on how certain we should be before we act or accept a conclusion. So that's just one way in which these sorts of standards for when we're acting on inductive inferences can change based off what we're actually using the inference for.
Are there I like that, the idea of I guess like an asymmetry between the results depending on your conclusion. Are there other good examples of that? I guess from the medical field, one of the big differences that I think about is, for example, the difference between observational research and clinical trial research, where obviously the results of clinical trials are considered to be less tenuous than the results of observational studies and things like that. And that seems reasonable. But back to the question, what I think is more interesting, the one that Joseph brought up, what are some other examples from other fields about these sort of like asymmetries between decisions? I guess we could flip that one and also say, there's the asymmetry between if a drug is known to not have any really poor effects and therefore you approve it, that like if you know that the drug won't have negative effects but has some chance of an upswing, then you're better off. Then you might be better off approving it so that people at least have a shot at it. And the worst case is that they try something that's ineffective. And of course, I know that socially, it sort of grinds our gears a bit. The idea that an ineffective drug might be put out on the market because obviously there's some profit incentive and things like that, and that bothers people. But at the same time, if it's sort of like there's no downside to a drug, but there might be a potential upside, then that might actually swing it the other way. Although it seems that we are generally, our main regulatory concern is usually don't allow unsafe drugs and don't allow ineffective drugs, not roll the dice on the upside. But what are some examples of these asymmetries in other fields?
Well, so in social scientific or psychological measurement, which I've been looking at quite a bit in my research, there are multiple examples of these kinds of asymmetries. So, or this kind of this process or the problem of weighing whether or not we have enough evidence or whether or not we can be confident enough in our evidence to base our decisions on them. So psychological measures are used to make decisions about which schools a person gets into, or which drugs a person is being prescribed. So when we're measuring, for example, mental illness, and when it comes to determining who gets to go to a specific school, you can have like tests of intelligence, or you can have tests of like characteristics of the person's personality or stuff like that. And yeah, so these measures are or have been used throughout history and are still used to make decisions about who gets to do what and who needs to take a certain drug and which drugs are allowed on the market and who gets a job. So personality testing has been very prominent in kind of like, or at least used to be. It's probably a bit less now, but there used to be a time when like companies really used very much of these personality tests to determine whether a person is fit for the job. And of course, there are problems with the measurement of the human mind. People are kind of like, you know, our behavior is hard to predict, and it's hard to read the measures precisely. So if we read the measures wrong, then we might make the wrong decision, and that might have really bad or really good consequences for the people whose lives we are impacting with those decisions. So there's plenty of examples there.
Yeah, when you said that if you read them wrong, it might have good impact on the people involved, it reminded me of that there's some 90s movie about the Flintstones remake where Fred Flintstone gets his sort of aptitude test incorrectly read and then gets shot up to become a manager simply because they read his aptitude test wrong. So that's the example that popped up. But yeah, it is interesting. And again, this brings up the sort of the induction, abduction aspect of this, where I guess when you're talking about, I guess, aptitude tests or personality tests, that, you know, there are these components where there are very strong correlations between certain types of personalities and what field they might want to go into, or the way in which they like to work. But at the same time, there are people who strongly deviate from these things and they sort of get missed by these same metrics. So similarly, like you're trying to find these correlations between these aspects, but to use those as if they are certainties, you know, to, again, as your example, to take an induction and to start treating it like it's a deductive truth leads to, you know, some pretty, I guess, I won't, catastrophic might be too strong of the word, but it leads to some pretty big missteps in logic. So you could just imagine that if you are using something as bland as like bland isn't the right word, but, you know, as ham-fisted as an aptitude test that only measures, for example, on a mathematical aptitude, but then you're missing out on, for example, like interpersonal aptitudes and I guess would be like social IQ and was it emotional IQ is the one. Obviously that's the one I guess I missed because I couldn't remember the word. But yeah, or verbal intelligence and things like that, where if you have one of these assessments and it does heavily favor one of these skills and then calls that the generalized intelligence skill, then you're missing out on all these other components of human capability. Also, I've read some where like there's the stick-to-itive metric, so like how tenacious people are, and that's pretty much as big of a thing for measuring someone's success, like whether or not they're just tenacious and won't stop, as opposed to actual like having a high level of like intellectual aptitude. But I think I've gone on too long. but it is certainly an interesting thing. Huub, did you have anything to add?
So I wanted to add an example from economics, where you can also see that for some time, something that people thought, so one metric that was considered very important in analyzing whether the debt of a government was sustainable was that it shouldn't be above 90% of GDP. The worry was that then you would get into a debt spiral because you couldn't fund your public debt anymore. Countries would start to distrust you and not lend you any money. But after the 2008 financial crisis, that actually became much more contested. So additional research suggests that the whole story is much more complicated. It also depends on how your debt is funded. So if it's largely domestically funded, you can have a much higher debt to GDP ratio with very little problem. And also
like Japan, for example. So like Japan, who has like I think
Japan has like above 200%, which also shows this how important it is, and that we're trying to. So we think we have a good explanation, but there are all kinds of factors that interplay. And once we look into that in more detail, it turns out that the story is again more complicated. And I think that's what this shows. Yeah.
Very cool. And yeah, so I think I think that also does show how. So, for example, if we again look at something like economics, where we think that we have this very strong correlation, or we have a very strong understanding of the mechanisms involved. But when things change, when you have something like a catastrophic event like the 2008 collapse, and we think that, oh, well, given the metrics that we have, all these metrics are changing, and yet the overall outcome is not changing, that then obviously that there's other components of this that aren't as well understood. Whereas, for example, if you take lab science, for example, where it's where presumably you're having these very controlled tests and you're only changing one parameter at a time, that we should have a better understanding about what the effect of a single parameter change is. Compare this to social sciences, where you're never changing one parameter, and that you're very rarely changing just one parameter. There's always multiple things changing, and you have to try to account for those correlations. The next thing that we're going to talk about is an interesting aspect that Elina has brought on, which is how induction, for example, can seep into deduction. And so basically nothing is safe. And I think actually we got a pretty good example of this earlier in the series with the issue of the deductive failure that I made in patient monitoring, where essentially I had this thing that seemed deductively true, but because one of my premises was based on previous observations and those inductions were not true, that in fact my deductive mode of reasoning failed. So it's a bit of a deeper issue, but Elina is going to lead us through it now.
Right. Okay. Yeah. So so the general form of the problem is that in a deductive argument, as we have mentioned several times, like if the premises are true, then the conclusion is true. But then, of course, there is the question of whether or not those premises are in fact true. And if those premises contain inductive claims, then the problem of induction, or the difficulty of kind of being very, very certain, or at least more or less certain about the truth of your conclusions, it kind of becomes the problem of that we're dealing with in the realm of induction becomes a problem that we have to deal with also in the realm of deduction. And there are other examples of this. So if we only think of mathematics as an example of deductive reasoning, then we might be led into thinking that every time we have a deductive argument, then we can be like, just by virtue of it being a deductive argument, or it being called a deductive argument, that it's like a very solid grounding for going forward. So another example is that a lot of times our deductive arguments are given in a formal manner. So, for example, if we give a mathematical argument, then we are using these x's and y's and these uninterpreted symbols. But as soon as we give the symbols interpretations, we have to give kind of empirical interpretations for the assumptions that we're making. Then it might turn out that the deductive inferences that we've carried out on the formal representation of a situation, they might not fit the situation that we're actually trying to explain with the formal model. So that again brings in issues that are not kind of the focus when we're talking about deduction at the kind of like basic level. So yeah. Just the point is just that there's more to deduction than this basic level of certainty that it seems to carry.
Just to make it is the idea. I like the idea behind that when we can have these formal X's and Y's and provide a true deductive conclusion in the formal sense. But the moment we try to turn those X's and Y's into real world properties, things like, mass, height, weight, conductance, length, things like that, where the properties of those real world entities then means that our deduction is invalid because those have further constraints on them, for example. Is that the idea behind this, that actually the deduction becomes invalid in the real world setting?
Yeah, so the example that I'm going to give is from psychological measurement. And so, for example, when we're looking at the reliability of psychological measures, for example, measures of intelligence or measures of depression or something like that, there is this background theory that has a formal, there is a formal theory. And in that theory, we make assumptions about what kind of error would be allowed for that theory to be applied in a certain kind of context. And there are other assumptions about how different testing situations relate to each other, namely that people don't change in between those testing situations. And so those assumptions are needed to derive certain kinds of measures or indices of reliability. So the mathematics behind the theory or the indices works nicely. But then, of course, as soon as we come into the realm of actually measuring psychological attributes or psychological phenomena, then those assumptions are going to be violated. And so that creates some issues for interpreting the indices that have been derived on the basis of certain kinds of assumptions. And so that is one of the examples of where we have a nice deductive argument, but then as soon as we apply it to a real world phenomenon, then it doesn't invalidate the argument. The argument continues to be valid, but it's just a matter of asking ourselves whether or not the assumptions are fulfilled in the empirical situation sufficiently for us to kind of warrant bringing the indices that we've derived in theory to practice. So no, it's not. It doesn't invalidate the argument, but it's more a question of like applicability and what can we interpret? How can we interpret the results?
Yeah, that's really interesting. And actually, as you're talking about that, it was making me think about some of the other work in medical science that I've seen where we actually do create like applicability indices and things like that to try to better understand where our conclusions, for example, two quick examples, where in a Bayesian context where we have priors, and the question is, well, are those priors actually legitimate priors? Like, do they actually describe our prior information given the new subjects to which they're being applied? So they're actually, there are indices. I think in a previous conversation with someone who works with the FDA, they talked about using these for clinical trials. Another one is in machine learning very frequently, where we actually have these indices where we do know that the mathematics of a certain algorithm works perfectly under certain circumstances. But when it starts breaking down, we can't mathematize all the different ways in which it can break down, but we can try to create sort of indices around applicability for those. And so it's one of those things where it's just like, yeah, there's a limit to where we can deductively get what we want. And then after that, we just need to identify what are the scenarios where this still applies. So it is interesting. And while I understand that what I'm discussing isn't, obviously directly related, isn't directly applicable to what you talked about, it is interesting how in these different fields, people are trying to essentially grapple with these similar ideas in their own fashion. So So similar. They're trying to cook a similar thing. They're just using slightly different cookbooks to come up with their recipe. Cool. Huub and Joseph, did you want to add anything to that, or are you set?
Do you want to open another can of worms? I mean, I'm happy to add stuff.
Oh yeah. How about for the next maybe for the next can of worms to open up, we should do here's a question. Science, it's based on induction. We've pretty much said before that induction is not guaranteed, and yet our scientific methods seem to work pretty darn well in describing the world. Why is that? And by the way, just a very quick interjection thing. One of the most fun things I found about like talking to philosophers, because now I've talked to quite a few of them, they all pause and think before they speak. And I think that that's very interesting and something that I personally can learn from. But it's been really fun talking to, I probably talked to probably about 20 philosophers now over the course of creating the series so far. And all of them, when I ask them a question, there's always like a pause and they think first, which I really enjoy. Scientific reasoning, or the scientific method, why does it work so well to describe the world that we see around us?
It's a trick question, because what is the scientific method?
Yes.
How do we characterize the scientific method?
Let's do that first.
What is the world around us?
Yeah, what is the world around us? Why don't we actually address that first? Because actually that's something that I've been meaning to talk about. People typically, when they talk about the scientific method, they talk about it's loosely in their mind what they mean is something that's sort of like a little bit Baconian, a little bit like a math, a little bit of like experimental design and things like that. But really it's sort of a collection of different methodologies that we use. And so that we're cobbling together different sort of good ideas about how to assess scientific statements and things like that. But what would we say what would make a method scientific?
Like you said, I think a scientific method is a collection of the various things that have been tried and that have been tested in various circumstances in various fields. And so because of that, and because there are so many different fields, so many different things that we can study, so many different methods, some of them are inductive, some of them are mathematical, some of them are armchair-based thought or theorizing exercises, so because there are so many, we can't really like give a general characterization that goes beyond saying it's the collection of the things that we have tried and tested in trying to figure out what the world is like. But beyond that, you can kind of specify it by talking about the desire to be objective, whatever that means. There's a lot of different ways in which we can understand that. And then there are these kind of concrete, practical methods that scientists have devised to make sure that the results, that whatever method we're using, that the conclusions are reliable, or at least somewhat reliable, that they're valid and stuff like that. And one of those practices is, of course, peer review. And so I think that to kind of summarize the idea is to say that scientific method is a collection of various things that the kind of reliability and trustworthiness of which are continually being tested by various different practices that scientists have come up with to kind of ensure that we're getting at knowledge and understanding and all those epistemic virtues that we want science to have.
And just because we're just cracking open cans of worms right and left, what about pseudoscience, for example? Is pseudoscience best defined as sort of just some counter to that? So it's the absence of some of these scientific virtues? How would you describe that?
So the question of, the difference between science versus what you're calling pseudoscience. I think this links up fairly well with what Elina's video is about in deductive reasoning. So One of the biggest 20th century philosophers was Karl Popper, and his main claim was that what pseudoscience is that, or what science is rather, is that it's putting forth theories that can be falsified. So a very basic structure is, if P then Q, not Q, right? From Elina's video, we know that the form of that argument therefore leads us to conclude that not P, right? So if you have a theory, it implies that this conclusion should be true. That conclusion is not true. We should therefore reject that theory or reject that hypothesis, right? And so science is a series, on his view, science is a series of putting forth these theories or hypotheses and then testing them and then figuring out which ones we can falsify. And so one component of what's called pseudoscience is that even in the face of contradictory evidence, the initial hypothesis isn't rejected. So astrology is a good example. This comet is going to fly over at this date, and that's going to mean that we're going to have a really good October. And then October isn't very good as a month. And rather than saying, okay, our theory about the relationship between comets and how good our month is false, we come up with a different explanation to say, oh, well, it just wasn't raining that month, so we can still keep our initial theory while ignoring the contradictory evidence. So that's sort of one way to draw the distinction between what's science and what's not science. And I suppose it links up with Huub's video as well on inference is the best explanation. So, in thinking through what is the best explanation for a particular set of observations, it's important to keep in mind, we should be willing to reject our initial theories when we have evidence to the contrary.
Very cool.
Yeah, I think Joseph is explaining completely like in line with what I've also been taught about one of the ways in which you can differentiate pseudoscience from science. But then, as always with philosophical questions, there are further difficulties with this kind of criterion of demarcating pseudoscience from science. And one of the difficulties is that there are a lot of cases where even if our evidence seemingly falsifies our theory, we kind of hold on to the theory because there are other aspects of so there are, for example, implicit background assumptions that we feel like that would be more reasonable to reject rather than the theory itself. So so falsification in that sense, we need to kind of further characterize falsification to then get rid of these examples of what we do regard as genuine science, where in fact where at least it looks like we haven't kind of like rejected the theory just because there was some falsifying evidence. So yeah, that's just to point out that these kinds of debates are almost never complete, or there's always more to be said about them.
Yeah, and I guess one example of that where you talk about, and this is an extreme example where you don't always reject, for example, good theory in the light of new evidence, one, because evidence can be corrupted in some way that you haven't accounted for. But I guess a really just simple example is, imagine I, on a piece of paper, drew a bunch of right triangles, and we measured those right triangles, and then we compared a squared plus b squared. Does it actually equal c squared? And I, take out my, 1-inch ruler to make that, to make those measurements. Well, I can tell you right now, no, my a squared measurement plus my b squared measurement is not going to equal my c squared measurement. That doesn't mean that we throw out the Pythagorean theorem. It's because we know that there are other confounding factors in our measurement process. And I guess you could call it our experimental process that will cause that our evidence would contradict what we know from the theory. But the fact is, we know that the theory is true, and we know that because of the deduction. And I think also, for example, in economics, there are many cases where we say, for example, that we know that logically certain phenomena only move in certain directions. So, for example, obviously you can't be increasing the price of something while still also allowing more people to be able to afford it. And so that there's a natural monotonic relationship between certain variables. and that no matter what the actual evidence says, we aren't going to make conclusions. We might say, oh, well, our understanding about exactly how much these monotonically related things correlate with each other might change. We don't actually change our understanding that these are monotonically related in some way. So examples like that, and I'm sure that there are plenty of others in, well, I guess biological sciences, there's quite a few where we know that, for example, cell interactions or intracell interactions and a lot of the intracell functionality, it operates in a certain way. And that no matter what your lab test says, if it contradicts what we know about the actual functioning and mechanisms on the cellular level, we would probably generally choose not to believe that. Now, of course, with the review process, people might ignore that, or they might not know about certain mechanisms enough that they understand that there are these other confounding theories and components that would actually nullify these experimental results, but still they are out there as a form of reasoning. So yeah, I think you've brought up some really good points there. All right. Well, we've covered quite a bit. I've really enjoyed this conversation. I think that I've learned quite a bit, and I think that these are exactly the type of conversations that I think data scientists should be interfacing with quite a bit more. Now, of course, the real main event is coming with each of your fantastic, gentle introductions to these topics. So to get more of a formalized understanding about how we do deductive reasoning and some of the components around that, how we have inductive reasoning and some of the caveats that are involved in inductive reasoning, and then abductive reasoning, and seeing how even Sherlock Holmes can get some of his reasoning wrong. Or at least not describe it correctly. So anyway, thank you each for what you've contributed to the series. I really appreciate it. Again, a final round of applause for Elina for pulling it all together. But I think we have 3 great presentations ahead that will be really good for people to watch. So thank you each for showing up today and for your presentations.
No, thank you.
Hey guys, it's Glenn. Thanks so much for listening to this most recent episode of the Philosophy of Data Science. I hope you enjoyed it. If you did, please consider leaving a like, a comment, and hitting that subscribe and bell button. We're a small channel and every bit helps. If you have a lab, a department, some students or some colleagues who you think would enjoy this episode, please consider sending it along. Again, every bit helps and we really appreciate your word of mouth. Our next episode on the Philosophy of Data Science will be coming out 1 p.m. Eastern Time, Wednesday of next week. So we look forward to seeing you then. But if you can't wait to get more data science, machine learning, and statistical content, feel free to look around the rest of the channel. We have a large number of playlists, including things like machine learning for healthcare, ethics and AI, and things like that. So give a look around. There's plenty more content for you to enjoy. You can also check out our website to not only see past episodes, but what's coming up, and see who our sponsors are. Thank you to our sponsors for your support. Now, while the views discussed on the show typically range between extraordinary and mind-blowing, the stated views don't necessarily represent those of the host, our sponsors, my employer, your employer, the speaker's employer, or anyone else not saying those words. And as always, thank you so much for your time. I really appreciate it. See you next week.